Hello, so I'm going to go over the fourth problem from the first problem set of David Tong's notes. So we have this Lagrangian here, and the first thing to note about it is it's basically, so we're summing over A here, so this is just a sum of three Klein Gordon fields. So each field will satisfy the Klein Gordon equation. So we're asked to show that this Lagrangian is invariant under this transformation. So this is like a rotation between the different fields. So if we just plug this in, so I'll just focus on this term here. I plug this term in, I will get this kind of thing. And I will FOIL this, so just a note, so I have these derivatives. When they act on this term over here, the only thing that depends on the coordinates is phi. So I will just get, so for this term here, it's just this d mu phi c, and then I get the d mu phi a from this term. Now the first term is just what, the ordinary term that we get. And then we get two terms that look like this. And then the last term will be quadratic in theta. So we just throw that away, say that it's very small. So we have these are the two cross terms. And we can notice that they both contain a d mu phi c, d mu phi a. The only difference between them is that here the mu is up for phi a, here it's down for phi a. But that if we're contracting two things, again, it doesn't matter which is up and which is down. So these two terms are the same thing. So we just have to worry about one of them. So I'll just worry about this. So if we look at this, and basically if it's invariant under this, then we should just have that this is 0. So I'm going to throw this theta away because it won't affect whether this term is 0. So if we just look at this, so I'm going to do something that is very common to do in when working through index notation problems. So we want to show that this is 0, and the way that we're going to do that is show that it's equal to minus itself, because 0 is the only thing that's equal to minus itself. And to do that, I will just swap around the c and a on this anti-symmetric tensor here. That will give me a minus sign. And then I will just call a c and call c a. And I can notice that, this term is the same as this term, only with the minus sign. So I've proved that this is equal to minus itself, and so it must be 0. So I won't do this term because it works out pretty much exactly the same way. Basically, we'll see that whenever we have in this anti-symmetric tensor, and then we have our two things that are the same, that are multiplied together. So in this case, they're both d mu phi's. We'll always be able to play this game. So in this case, I would have two phi's. So I can do the same kind of thing here. So the Lagrangian will be invariant under this transformation. So now we can compute our conserved current. So since this is basically just the Klein Gordon Lagrangian, it's very easy to do that. This derivative will just be d mu phi a, and then we're just given delta phi a as this. And so computing the divergence of J here, we want to show that j mu is conserved. So we compute this. So we have two things that depend on the coordinates here. We have this phi and this phi, so we use the product rule. So this term will be d mu phi a. This term, the d mu will act on phi c. So again, this term I have two d mu phi's here. So I can play our game, set this, prove that this is able to minus itself, and therefore it is 0. So I'll just be left with this term. But then I can use the equations of motion. I know that phi satisfies the Klein Gordon equation. So I can replace this d mu phi a with negative m squared phi a. And then once again, I have phi a and phi c, so I can show that this is 0. Another thing I can do here, a subtle point is, so if I have this and I write out, if I do the sum over b, I will get 3 terms here. So here b is 1, here b is 2, here b is 3. And each of these, with each of these terms, I can play the game of showing that it's equal to minus itself. So basically, each one of these terms is 0 separately. So that means that we have our conserved current is really the sum of 3 conserved currents. And so we can write the bth conserved current as this expression. And so there's some room for confusion here because this expression I've written here is exactly the same as this expression. But in this expression, I'm summing over b. And I'm saying that the bth term, here I'm saying the bth term in that expression is given by this. So here I'm not summing over b. Here b is either 1, 2, or 3. So this is so I have 3 conserved currents, one for each value of b. And so now I can compute my conserved charges by integrating, so the bth conserved charge will be the integral over the time component of the bth conserved current. So the 0th component, so I'll just replace this mu with 0, so this is time derivative of phi a. So our conserved charge will be this. And okay, so now what I can do is, so again, in this expression, I'm not summing over b. So in b here, it's just a constant. And if I have a conserved charge, QB here, then I'm free, that's basically saying that the time derivative of this is 0. But if I multiply this by a constant, that expression will also have a 0 time derivative. So I could call that my conserved charge. So I'm free to multiply and divide to redefine my conserved charge. So since I'm not summing over b here, this nb is just a number, it's just a constant. So I can redefine my conserved charge as this divided by nb and just be left with this. So now I can, so just to get to the expression that David Tong has, I can exchange a and b here on this tensor. So I'll get a minus sign, and then I will just call a b and call b a. And I will have an expression that looks almost like David Tong's expression, except I have this minus sign. But again, a minus 1 is just a constant. So I'm free to redefine my current, multiply by -1, and I will arrive at the expression David Tong has. So the only thing left to do is show that this is actually conserved. So show that its time derivative is 0. So if I take the time derivative here, I will get a product rule, and I'll have these two terms. So since I have two phi dots here, I can play our game, show that this term will just be equal to minus itself, so this goes away. So I'll just have this. And this, so I can use the equations of motion. So, the equations of motion are d mu plus m, d mu phi plus m squared phi equals 0. But d mu phi will be phi double dot plus di phi, where I is just summing over the spatial components, plus m squared phi equals 0. So basically I can replace this phi double dot with minus di phi minus m squared phi. So that's what I've done here. So then the second term, again, I'll just have a phi and a phi. So I can throw this away, play our game, throw this away. So I'll just be left with this term here. So I'm left with this. So now I can integrate by parts. So clearly, if I take the derivative of this, I will get, di. I'll get a product. Well, you know how to integrate by parts. I just integrate by parts here. So you can show that this is equivalent to this. But so now I have a di phi and a di phi. So this term will be 0. So I'll just be left with this term. And this is the integral of the divergence of this thing over all space. But that basically means that I'll be evaluating this at the boundary of our space. But we're assuming that phi and its derivatives behave nicely, so we would assume that at the boundary, phi and its derivative should go to 0. So we're just going to assume that is the case. And if that is the case, then this will just be 0. So our conserved charge is conserved.